you know whatever I have discussed is a N channel JFET, N channel configuration JFET. We have not discussed about P channel. We are discussing about only keep in mind N channel JFET configuration, N channel JFET device, N channel configuration. As I have discussed, the third case, VGS is equal to 0 and you are increasing VDS from 0 to certain voltage. What I am doing here on the x-axis you can see what is our x-axis, VDS, drain to source voltage. That is I am increasing from 0, 1, 2, 3, 4, 5, 6, 7, 8, whatever it is, 0.1, 0.2, 0.3, whatever it is. We are increasing in equal steps. And we are noting down or we are seeing what will happen to the output current, that is your drain current, which I have given, which I am measuring in terms of milliampere. The VDS is in terms of voltage only. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 volt. Maybe hardly 5 volt or maximum voltage is 10. So when you see the third case, in the third case, what will happen? Your PN junction diode, the JFET will be under forward bias condition, which causes there will not be any depletion layer. Depletion layer fades. Depletion layer will become 0. It's gonna fade away, vanishes. So this is your channel. Your channel will look like this. If it is a rectangle, the channel will look like a S shape. This is completely channel. And in the yesterday's class, in the diagram, here I wrote B, here I wrote C. That is B to C. The complete is the channel. So area of the channel here XC, that gonna reduces. When the VDS increases, area gonna reduces. Means majority carrier will travel from B to C, from source to drain, which is causing the increase in your drain current. Which is causing the increase in your what? Drain current. In the graph you can see drain current is increasing linearly. This is your P point. This is O. This is not 0. This is O to P. The curve that is look like a linear curve, maximum curve, increasing rapidly. Understandable? As VDS increases, length of the channel, area of the channel like C, that gonna reduces, that gonna decreases. That may increase in our output current. Our output current is drain current. Understandable? Say so. So at a certain voltage, I will repeat, at a certain voltage, I am marking this, at a certain voltage of VDS. What is this? VP. At a certain voltage VP of what? VDS. What will happen? Your drain current will increases maximum point. Here. What is this? This is your maximum point. So at this voltage, your channel is going to pinch off. We will say a technical word, pinch off. The channel or area will become less. That is going to pinch off. This voltage is called as pinch off voltage. In the previous case, when we have a reverse voltage, channel is going to cut off. But here, channel is going to pinch off. Area will become somewhat smaller. And technically, we will call it as a pinch off. And this voltage VP, which is denoted by VP, that is your pinch off voltage. It may be any voltage. It may be 1, 2, 3, 3.5, 3.7, 4, 4.7. We don't know. Practically, it may be anything. At that voltage, your area will become less. Your channel is going to pinch off. That's why that is called as a pinch off voltage. Understandable? Got the point? Say sir. So this is value of VDS only. VP is the value of VDS. At this voltage, your channel is going to pinch off. That voltage is called as pinch off voltage. Now let me explain you what are these areas. What do you mean by ohmic region? What do you mean by saturation region? What do you mean by breakdown? Why breakdown is occurring in the device. Focus here, as simple as it is. If you are able to draw the graph, you can define them very easily. If you know the graph, if you remember the graph, or if you completely know the graph, you can define what do you mean by ohmic region, what do you mean by saturation region, what do you mean by breakdown. That you need a technical points. I'll tell you. What is the first region? Ohmic. See here, the space which is available from, first one is ohmic region. The space or the region which is available between or which is available from VDS is equal to 0 to VDS is equal to VP. I will repeat it. The region or the space which is available from VDS is equal to 0 to VDS is equal to VP. Simple thing. That area, that region is called as ohmic region. And in this region, the current is increasing rapidly. Focus here. From here. I have dotted line. I have drawn a dotted line. This looks like a PN junction diagram, the forward bias condition graph. Focus here. The current is increasing rapidly. Current is increasing linearly. We say it is a linear graph. You know what do you mean by linear graph? I don't need to explain this. This is a linear graph. Because of this reason, in this region, I'm telling because of this reason, in this region, in this area, your JFET will work like a variable resistor, variable dependent resistor. In real time, it will work as a variable resistor, variable dependent resistor. Means they will take this device in ohmic region. It will work as a variable resistor. You can vary the resistor. In certain application, we have to vary the resistor. That time, they will incorporate this JFET in a ohmic region. Understandable? Because here clearly I can say that we have a resistance, that is drain to source resistance RDS is equal to ID divided by VDS divided by ID. Here R is equal to V by I. V is VDS, I is ID. That is a resistor. Here clearly we can find out resistor. Here V, here I, here V, here it is I. You can make a contact, intersect it, you will find the resistance value of R. Understandable? That's why in this region it works like a variable resistor. Device will work in real time variable resistor. Clear? Say so. Got the point of ohmic region? Let me move to saturation region. In the diagram, just look the diagram. The region beyond VP, the space after VP. In common words, you can say after VP, but technically we will say the region, the space beyond VP. That is called as saturation region, or you can say pinch off region. This region is called as saturation region or pinch off region. One more definition. In this region, look at here, what is happening to ID current? Good. What is happening to ID current? It is constant. See here, if it is 5, it is 5 only. In this region, only specially about in this region. This is constant. This is constant. This is constant. There will not be no change in drain current. If you increase VDS beyond VP up to here, clear? Up to this area is pinch off region or saturation region. Understandable? Say some as simple as it is. Just look the diagram. You mention the region, you mention the space where it is available. Beyond VP it is saturation region. One more thing you have observed that your drain current is constant. Your drain current is constant. Here drain current increases. Here it is constant. Nothing change in the drain current. Clear? Say some. Say some. What is last? Very long back ago, in the olden days, I explained you how does breakdown occurs. In the PN junction diode, I explained you how does breakdown occurs. Anybody in the we can recall it. How does breakdown occurs? How does breakdown occurs and why we are calling it as a breakdown voltage? What do you mean by in common breakdown means what? What do you mean by in common breakdown means what?
Breaking the PN junction.
In PN junction diode, long back ago, I explained you how the junction breakdown occurs.
Increasing the electrons.
Reason here, what will happen? Focus here. At a certain point, this point. At a certain voltage, at a certain point B. What I am telling? At a certain point B, at this voltage, that I have denoted as VVDGO. At a certain voltage, after given VP, at this voltage, what will happen? Majority carriers between gate and drain. On the right side, what we are having? This is gate and this is drain. The majority carriers, or there will be an increase of avalanche of multiplication of electrons. I am telling multiplication. 4 into 4?
16.
How much?
16.
16. 16 into 4?
30.
64. Like that, avalanche of multiplication will happen. Because you are increasing the drain to source voltage, that will cause a increase in number of electrons. What are the majority carriers in N? Electrons. They will increase between gate and drain. Here they want to increases, which causes breakdown. If electron become more, if they are more, for example, you have a very small space. You have only space, small space, and you are putting something or you are adding some coins. If it is become, you are adding more coins, what will happen? That piggy bank will break. Something will happen. Like that, if the number of electron increases, breakdown occurs. Again, that will cause a increase in the drain current. See here, your drain current is increasing at this point. Say sir, here it is constant. Again at B point, at this point, your drain current is increasing. So, the voltage at which here the breakdown occurs, that is called as breakdown voltage. That is denoted as VVDGO. Here, as simple as it is, that breakdown again we will have a maximum current. Drain current will increases because number of carriers has been increased. Number of electrons has been increased. We call it as the avalanche of electrons. But in this case, it is avalanche of multiplication of electrons. Previously, I have said 4 plus 4 will become 8, but here multiplication. They will become more. That is causing the junction breakdown. Here, understandable? Yes, sir. These are nothing but drain characteristics of your JFET. If you remember the graph, as simple as it is, in your own notes also you can write down this. What is ohmic region? What is saturation region? In the graph only everything is available. In the graph only answer is available. You have to look for it. You have to see some notes. You have to keep your mind. You have to attend your classes. Done? Any queries? Any queries?